Bismillahirrahmanirrahim. Assalamu alaikum dear students. Welcome to the online lecture on MATLAB simulations of control systems. Today we are going to discuss this conference paper which is about the output feedback integral optimal sliding mode control for magnetic levitation system. This paper is a recent paper published in the proceedings of 4th International Conference on Inventive Systems and Control. So let's see what we have here. So first of all, we are not going to go through the details of the paper and introduction section. You can download the paper and read it by yourself. So here we are interested in the modeling of the system and the simulation of control. So we go straight to the modeling. So modeling of magnetic levitation system is done in two parts. I actually have a video about how we can model a magnetic levitation system on YouTube. I will share the link in the description of this video. But anyways, first part is that you have this mechanical force is equal to mass times acceleration, the force balance equation, and then you have the power balance equation where electric power is equal to mechanical power. Here is the description of the system. You have the electromagnet, and electromagnet exerts this force on this metallic ball, and on the other hand this metallic ball is undergoing the force due to gravity as well. So you have to strike the balance between the electromagnetic force and the gravitational force to position this ball anywhere at a fixed distance x from the magnet. So this is the control problem that is discussed in the magnetic levitation systems. So after the derivations and the simplification of equations, here is the dynamic model of the magnetic levitation system. It has three states. So the first state is the position of the metallic ball, which is x1. So the derivative of the position is equal to velocity, and then the derivative of the velocity is equal to this whole thing, which is g is gravitational constant, k1 is spring constant, m is the mass of the ball, and this x3 state is the current through this electromagnet. So this current flowing through the electromagnet basically determines the force exerted on the metallic ball. So that is why we have the current of the electromagnet as one of the state variables. So the derivative of the current, which is x3 dot, is equal to minus r over l. So this r is the resistance of the coil, l is the inductance of the coil, and then we have different constants and state variables involved in this equation. So in short, this is the basically the state space model of the magnetic levitation system for which we are going to design the controller. So before I discuss the controllers, the sliding mode control discussed in this paper, let me show you a very simple way of designing control basically I'm going to show you a PID control for this system shown in equations 15, 16 and 17. So let's go and see. So here we have so the value of k1, this is given in this paper, and value of mass, resistance, inductance, gravitational constant, all of these values are taken from this research paper, which are given if you go down here into the results section. So you will find all the values. So some of the values are here. So you see gamma 1, gamma 2, gamma 3. We will be using these values later on, and then other values are so control gain is also given, and also the mass, inductance, some of the values are given here, the mass, gravitational constant, k1, resistance, inductance. So all of these values are taken from the paper. So let's go back to our model and design a PID controller for this system. So here is the system, 3 state variables. So we are looking to get the desirable state. So we are looking to position the ball at 9 millimeters. So that is 0.009 meters away from the base. And since we are looking to fix the position, the velocity of the ball will be 0 at the desirable value. The desirable value of the current is 0.8 amperes, and this 0, I will tell you that if you have already watched my video on how to implement integral control on state space, you already know that we have to introduce a new state variable for doing that. So this 0 corresponds to that new states, which is the integral state. This control gain is also so this much gain is given in the paper. So the control gain for the 3 states x1, x2, x3, this is given in this research paper. So I've taken it from here. The 4th gain part I have assigned the value by myself. You can assign the value or obtain the value by placing the poles. And if you don't know how to place the poles in state space, I will share the link of how to design the integral control for state space based systems in the description of this video. Then the control is simple k times x desired minus x. So the control, this is not the control I have taken from this paper. This is simple PID control. So here are the dynamics of the state variables. x1 dot is equal to x2, x2 dot is equal to this equation which is taken from here. Then x3 dot is equal to this equation number 17, and x4 dot, which is the integrator state, is the error between x1 and the desirable value of x1. And then once you have this, then you can basically run this function by using the ODE45. You can use ODE45 or ODE23 or any other ODE solver in MATLAB. ODE45 is most common. So you can provide the name of the file. Here the name of the function is MAGLAB SMC test, although this is not an SMC controller. Anyways, we run it for about 2 seconds, give the initial conditions. These initial conditions are also taken from this paper, and then we have this desirable value and k. So these are used here for calculating the control input, because I also want to show you what control efforts are involved in this PID control. And then in figure 1 we plot the position versus time, and then we plot the current versus time, and then we so remember, we want the position to be at 0.009 and we want the current to be at 0.8 amperes, and then this control input will show us how much control effort is exerted. So these are the results. So this is the control effort. You can see that the maximum magnitude of control effort is 1.8, and it goes all the way down to 0.4 or even less than 0.4, and it is settling at some value. So this is control effort. This is figure 2 is the current versus time. So our desirable value for current was 0.8, and you can see that we have 0 steady state error, and the desirable value is achieved in about 1 second. And if you talk about the settling time would be probably about 0.5 or 0.6 seconds for this controller. Then this is the result of position versus time. So this is the position of the ball which we desired to settle at 0.009 meters, and this is where exactly it settles down. So that is the simple PID control for magnetic levitation system given in this paper. And next we continue on to discuss the sliding mode controls discussed in this paper and see how those control work for this system. Okay, so we get back to the paper, and you can see here that this paper discusses the linearization of this nonlinear magnetic levitation system, and then the sliding mode control is discussed with the reference to this linearization. We will see how all of this works. So with linearization you get A and B matrices for the system, and the dynamics with A and B matrices are represented with the x hat, which is called the normal form for the system. And this is important, the sliding surface is selected to be the product of G and x hat. So G is some matrix G1 and 1, where the size of G1 is the number of rows in G1 is the number of inputs, which in our case is 1, and the number of columns is n minus m, which is the difference between number of states and number of inputs, which in our case is 2, because we have 3 states and 1 input, so n minus m will be 2. So G1 will basically be 1 cross 2, and if you add a third one on the same row, then it will be a 1 cross 3 row vector. So G times x, that is the sliding surface for our case, and G, this small g, G1, that is designed in such a way that A1 minus A2 times G1, that is Hurwitz. So you can use the place command. So A1 and A2 are the first row of the linearization of magnetic levitation system A matrix. So you first linearize this system, you get a 3 by 3 A matrix. In that 3 by 3 A matrix, basically there will be the 2 by 2 part of this 3 by 3 matrix will be such that there will be corresponding zeros in the B matrix. So the A1 is a 2 cross 2 matrix, and A2 is 1 cross 2 matrix. And once you use the place command, or use the pole placement methods to place the poles of this characteristic polynomial of due to this equation, to get the G1 values such that the eigenvalues are in the left half plane, then you can get the G1. I will show you in the code how this is done, but this is a more important thing, that when we are doing the reference tracking control, what we are doing is that we are basically stabilizing the error dynamics. So if you drive the error to 0, then that automatically means that x1 is driven to its desirable value, because the error is the difference between x1 and its desirable value. So keeping this in mind, this is our sliding surface G times x, and our control is given by 2 parts, U equivalent and UN. U equivalent is given by this minus GB whole inverse times GAX, and UN is given by minus beta sine of S. S is the sliding surface, given by this equation 23. So what we will do here is that we will implement this in MATLAB. So let me show you how this is done. So this is these are all again the same values that are used in the previous file, and here we have, since we have to use A and B matrices, the linearization. So let me just maximize this so that now I do this because the whole code is now available on your screen. If you want, you can take a screenshot of this part of the video and copy, type the code by yourself so that you can run it on your own computers. So this is A and B matrices given here. So here this is A matrix, this is B matrix, and all of these values, so this is the x1, x2, x3 values, which is the operating point at which we are going to operate. This is also given in this paper, and this is A11, A12 matrices that are discussed here for the for computing G1. We have this A1 and A2. So these are these matrices. These are basically the 2 by 2 part of A matrix, the first two rows and first two columns, and this is the first two rows and the third column. And G1 is place. So the paper itself suggests that you calculate the G1 by placing, you know, eigenvalues at -3 and -5. You can place eigenvalues at anywhere in the open left half plane and get the value of G1, and then G will be equal to G1 augmented with 1, and this is your sliding surface, equation 23, this one. And then you have desirable value of x to be 0.009 for the position, 0 for the velocity, and 0.8 amperes for the current. Your this is UE, which is given by if you go here, this is this equation 31, and UN is this equation 32. And then we have U is equal to UN plus UE. These are the same dynamics that we have used already. So this is our function file, and then this is our file where we call that function, and these initial conditions are also given in the paper. And these are the this is the code repeated from the function file just to calculate the control input U. And then we plot the control input and the position and the current. So I'm running this. So this is the result from the sliding mode control. You can see that within 0.35 seconds there is some chattering in the control, and after that this is the current. So it settles down in to its desirable value, which is 0.8 amperes, and this is the position, which settles down at its desirable value, which is 0.009. So this is the simulation of sliding mode control, the simple sliding mode control given here in the paper for the magnetic levitation system. Next we go further into the paper and implement the integral optimal sliding mode control and see how that works for the magnetic levitation system. So moving on to the integral optimal sliding mode control. So we have this nonlinear uncertainty related assumptions as is the normal case for sliding mode control design, and you have U is equal to UE plus UC, as we have seen earlier in this type of sliding mode control. The control will have two parts. Here the sliding surface is designed as this matrix G times X minus this in trajectory due to a partial control. So this is quite interesting part of this paper, because you can see here that x naught minus the integral from t naught to t f of x comma tau plus bu x comma tau d tau. This is the system trajectory when the nominal control UE is applied in the absence of uncertainties. So for this slide, for implementing this sliding mode control, you have to basically duplicate the system of magnetic levitation, and then you on one system you apply the nominal control in the absence of certainty, and the resulting trajectory is used to determine the sliding surface. So let me show you how this is done. So we go back to the next. So this is the code. Once again I maximize this so that you can take a screenshot at this moment and copy the code from this file. Then so these are the constants and so on. So you can see here that in the previous file we have only 3 state variables, but now in this type of sliding mode control we are going to have 6 state variables. So these 3 variables are the copy of the original state variables, to which we apply only the nominal control, and we use the trajectory of this system in the sliding surface that is used in the original system of these 3 states. So if we like show it side by side, so this is the sliding surface. So here the sliding surface is S is equal to G times x1 x2 x3, which is this x, minus x naught, this is the x naught. So there's and then this whole thing, this whole integral, this is going to be the states x4 x5 x6, which are basically the trajectory due to application of nominal control on the system. So this is the x desired value, and the nominal control is k times x desired minus x. So u is equal to kx would be the nominal control, and the gain k, once again this gain is given in the paper, and these are A and B matrices, the same matrices that we have used in the previous sliding mode control design. So this is UE is equal to minus kx, where k is designed using by solving the Riccati equation. So this is the LQR type control, and this is given in the paper, and UE is equal to minus kx is this equation. And then we have so we have UE1 for the reference trajectories and UE for the original 3 states, and then UC is equal to minus rho. So this is the control that depends upon the sliding surface, and this is given here. If you go down in the paper, so UC is this is the expression for UC, the equation 41, which is minus rho times GB transpose times sliding surface divided by the norm of the same thing. And equation 41 is written in the code like this. The value of rho is given in the paper to be 0.554, and then we these are the dynamics of the magnetic levitation system with the sliding mode control, and this is the copy of the dynamics with just the nominal control UE1. So you can see here that here I use only UE1, and here I use U, which is UC plus UE. Okay, then we run this system, and using the same coding philosophy that we have been using so far, this is the copy of the code from the function file, just to calculate the control effort, and then we plot the control effort and everything. So we run this file. It will take a few seconds to calculate everything, and then we will have our results. Okay, yes, so the results are here. This is the control effort due to this integral optimal sliding mode control, and you can see here that this is the current which is settling in about 1 second, and this is the 0.09, the desirable value. So the position of the magnetic levitation ball is also settling down. Well, somehow this is slightly slower compared to the sliding mode control that we used. It is supposed to be better than that, but I don't know. So these are but anyways, this is how you simulate the integral optimal sliding mode control, where the sliding surface is really an interesting way of designing a sliding surface, which requires us to have a copy of the dynamics, and we apply nominal control and use those dynamics to construct the sliding surface. And then the LQR is also being used as part of the control, so this is quite interesting. And then there is a scheme for chattering attenuation that we will not be discussing in this video, but this is really, I mean, you can do this simple adaptive thing and try to remove chattering in the control. Then at the end we have this output feedback sliding mode control. In this type of this is basically high gain observer based control. So what will happen is that we will be using the same control as we have discussed here, the same control that we have discussed here just now, but we will add some states of the observer as well. So this is how this is going to work. So this system is going to have now 9 states. 3 states will be of the states of the observer, 3 states will be the states of the system, and the 3 states will be the states of the copy of the system, which will be used to determine the sliding surface. And this is the code that you can, once again take the screenshot of this code and run it, type it yourself. So these are the equations that equation 62, 63 and 64. If you look at these equations, so x1 dot is equal so this is basically going to be x4. So x1, x2, x3 are the same equations, equation 15, 16, 17 that we have used in the sliding mode controls that we have discussed so far. And then you can see here that x4 dot is equal to this x4 is x1 hat in this code. So x4 dot is equal to x5 plus g1 over this epsilon value is given in the paper, and x1 minus x4 means that x1 is actual x1 and x4 is the x1 hat. So this is the x5 dot, this equation is basically equation 63 of the paper, x6 dot equation is equation 64, and then the sliding surface is given here. This is the sliding surface, and then in the sliding surface we have x hat, which is x4, x5, x6. Then we have initial condition, and then x8, x9, x7, x8 and x9 are basically they correspond to this integral here. And then u is equal to ue plus uc, which is given here. Ue is again the LQR type of control, and uc is the sliding surface based control law. And then you can run this system. So if I run this system, then you can see the results. So this is the control due to the output what is this output feedback IOSMC. So this is the control due to that. And then you can see here, this is the current. The current here for some reason is not settling at 0.8, rather it is settling at some other value. So there is a steady state error here, which could be resulting from anything. There might be some error in my code or something wrong with the equations given in the paper. So usually the equations in the paper are all correct, what happens is that while writing this complicated code, you miss out on something, or some variable interact with each other. So you have to really look at the code very carefully, and you can remove these little errors. So y value is 0.928. So there is a small 10% steady state error here. Instead of settling at 0.8, it is 0.92. And here again there is a steady state error, and it is settling instead of 0.09, instead of settling at 0.009, it is settling at 0.0104, which is a little bit, again 10 to 12% of a steady state error. But anyways, so far we have discussed like 3 different controllers, actually 4 different controllers, 3 out of which they worked perfectly, and the 4th output based control that is showing some steady state error in the plots, which we do not know yet why this is occurring. We are just okay. Now in the end, before I conclude this video, I have compiled a comparison file. Here we are going to call different functions. So MATLAB test was the PID control file, MATLAB test 2 was the simple SMC control file, and MATLAB 3 is the IOSMC control file. So these 3 controls have worked perfectly for our case. So we are going to compare these 3. So again, I just scroll this code up and down, so you can take screenshot of this part of the video and write this code in your MATLAB file, and then you can take screenshot of this part and then write the code. Then if you run this, then we can compare the 3 different controllers. So it is running, and then we have to wait for the results to come out. Okay, it's taking some time because of course we are running 3 different controllers, so it is going to take some time. So far we have just discussed almost everything that has been presented in the paper. So this is the result. So this is the control effort due to this black line, IOSMC. So IOSMC results in the least amount of control effort, and then integral control has also less control effort compared to the simple SMC. But on the other hand, simple SMC is really quick. So for example, this is the comparison of the stability result. So simple SMC basically tracks the value of 0.8 within 0.35 seconds, whereas integral control takes some time. And here this is something very interesting, because I am using the same file here. So I have compiled these results using the same MATLAB SMC test 3 file, which is this file. If I run this file using this script, then there is no steady state error. But if I call the same function MATLAB SMC3 in here, then there is some steady state error. You can see here that this is IOSMC is incorporating some steady state error, and the steady state value is 0.928, which is exactly the same value that we got from this IOSMC based file MATLAB SMC. So this IOSMC resulted in some steady state error. Sorry, what is this IOSMC. So output feedback IOSMC resulted in some steady state error, and the IOSMC is resulting in the same error if you run it separately in this file. But if you run it from this file, then there is no steady state error. So if I run it from here, then you can see here that it would take some time to run. So this you can see there, maglev SMC test 3, and I'm running it right now. So it is so these were the previous results which show the steady state. Now these are the results. So you can see here that there is no steady state error in either the position or the current, and I have run the same file. But if I run the same file here, then the steady state errors are the same that appear in the output feedback IOSMC. This is something quite interesting, and well, interesting things happen when you are programming complex systems. But anyways, I hope that this video was educational for you, and now you know how to implement magnetic levitation, implement the sliding mode control on the magnetic levitation system. And that is all for now, and we will continue our discussions with some new exciting control problems and the simulations of the control problems in the next video. Thank you for watching.